Okay, we are recording.
I guess we'll give people a couple more minutes.
Yeah, let's not start until right at the bottom of the hour. And Greg and David, I'll give the entire time slot to you. I will just say just a few minutes before the bottom of the hour, which is now, and just welcome everyone who's joined and remind everybody of kind of the ground rules of typing in their name and then muting and unmuting as appropriate. Oh, and Greg, you're welcome to go ahead and project your slides if you'd like. If you're first.
I'll start. Yep, I'll start. Sharing.
There we go. Yeah, and you can go into full screen mode, or sharing mode is usually a good one too. Yeah, that'll be fine. Okay, looks good.
So I'm going to have to do like a switch between slide decks because this is in a few different slide decks, but I'll try and do that as seamlessly as possible.
Sure, that's just fine. And I'm mostly, just for your reference, Greg and David, I'm mostly just going to hang out in the background and won't say or do much of anything. So I'll leave it mostly to you two, but please speak up if you need my help with anything, and I'm happy to try to help. But it should be pretty seamless, I think. And we'll get started here in just about a minute. So those who have joined, I'm just going to check and make sure everybody's got their first and last name typed in. And everyone is appropriately muted unless they want to actually have participate in the conversation, then you can unmute. Okay, it looks good so far. All right, I'm going to go ahead and turn it over to you, Greg, and then David, and you can take it away.
Great, thanks very much. And thanks everyone for joining us. So today we're going to be talking about developing a testing and continuous integration strategy for your team. This is a tutorial, so it does have hands-on activities, but we're not really going to have time for that today. So it's really going to be more of a presentation. The website here, which is the link on this page here, you can go to there for a link to today's tutorial, which has everything, the slides, the hands-on activities, and any last-minute changes. So feel free to utilize that resource. So I'm Greg Watson, and David Rogers will also be co-presenting. So I'm just going to get going now. All our presentations have this slide, which is license and citation and some acknowledgements on it. So you'll probably see this often. We're just going to jump over it. I will talk a little bit more briefly about this in a minute. David, do you want to just briefly introduce yourself?
Hey, I'm David Rogers, also from Oak Ridge National Lab, and I work in the science engagement section with users of the Summit and Frontier supercomputers.
And I'm Greg Watson at Oak Ridge National Lab. Also, I'm group leader of the application engineering section, group actually, which is part of the computer science and mathematics division. And we're both members of the Ideas Productivity Project and the ECP Ideas Project. Oops, sorry. Okay, so what is the Ideas ECP team? So essentially, we work with the ECP community and beyond the ECP community as well to other communities to help improve developer productivity and scientific software sustainability. And the idea is to, these two things are key to increasing overall scientific productivity. activities, customize and curate different methodologies for developing scientific software. We develop techniques for incrementally and interactively improving software practices. And I'll talk a little bit more about that. We also are involved in establishing software communities, and that includes helping communities determine policies to improve software quality. We work with communities to create software development kits and facilitate the combined use of complementary libraries and tools. And then another significant area is we engage in community outreach activities, including partnerships with communities, collaboration with computing facilities, developing webinars, tutorials and other events, documentation, and then also maintaining the Better Scientific software site. In terms of building an online community, the primary focus is this Better Scientific software site, bssw.io, which is really a central hub for sharing information on different software engineering practices and techniques and experiences. It's a community-based resource. It's not something that we primarily develop content for, but we collect information and content from the broader community and make that available through this site. The goals of the site are to raise the importance of good software practices, of the increasing challenges facing software developers of scientific software, help CSE researchers increase effectiveness, and facilitate collaboration as well. The site is useful for finding information on various scientific software topics. You can contribute resources based on your own experiences and create content tailored to the scientific domains that are of interest to you. If you're interested in participating more in ideas and BSSW, there's an ideas mailing list, which essentially is used for announcements of different events and so forth. It's very good, 3 messages per if you're interested in finding out more about what's going on. There's also the BSSW Digest, which contains updates on new content, blog posts and events and so forth that goes onto the BSSW website. And again, very low bandwidth. And there's also an RSS feed too, if you're interested in signing up for that. So that's easy ways to get connected with that community. I do want to just take a minute or two to talk about naming. Diversity and inclusion is very important to the members of the ideas community, and what we try and do is really strive to remove any terminology that may be considered harmful or exclusive or anything like that, and replace the language with more inclusive language. We try to do that not only for our documentation and for our software, but also for our tutorials and other communications. And so in this tutorial, we've tried to adhere to those principles. We welcome suggestions for improvements in this area in our tutorial. And there's a couple of resources there if you're interested in the naming, the inclusive naming initiatives and so forth, if you're interested in finding out more about that or getting involved in that effort. The BSSW tutorial website, as I mentioned, that's the go-to for information about this tutorial and also other past tutorials and upcoming tutorials that we're planning. It has the agenda, the presentation slides, the hands-on exercises and various other resources. So please utilize that that site, particularly if you want to do the hands-on exercises associated with this. We'd highly recommend doing that because that will help you better understand the concepts I think that we're trying to get across today. We have these hands-on exercises. We're not going to have time to really go into that today, but they're definitely and time, and that'll give you an opportunity to put into practice some of the things that we're talking about. We will give you feedback if you want to open issues or pull requests related to that. We'd be happy to accept those and provide feedback on that as well. Going back to the slide 2, that license and citation slide, as I mentioned, all our presentations will contain this. Was there a comment? Okay. It's best practice to make your license and citations easily findable, and also provide sponsor acknowledgement. So just be aware that this will be in all our presentations, but we'd also recommend doing this kind of thing if you're developing your own documentation and presentations. So we're really keen to interact with people rather than just present material. We want to share and learn from the participants of these tutorials, and about any experiences that you have. So feel free to use the Zoom chat if you've got any questions. If you do work on the hands-on exercises, as I mentioned, we'll be happy to give feedback. You can do that through submitting pull requests or issues. You can also email the tutorial email address, and if you've got any questions or you'd like feedback, would like to give us feedback or anything, we'd be happy to accept that, and we will respond to you. Okay, so I'm going to switch over to the next slide deck quickly. Overview. There we go. Zoom moves the slide decks around. Okay. So now I want to briefly talk about some background and I'll give you an overview of what we're planning to do and some motivation behind this tutorial. So our sort of guiding principle is that scientific computing, science now is predicated on computing primarily, and what you can achieve through science really is at best as credible as the software that produces it. And so if you really want to produce credible scientific advances, that stand the test of time, then the software really needs to also be credible and reliable and reproducible. And so that's really what underpins this tutorial. And we want to give you some ideas and suggestions on how to achieve. A couple of examples of consequences of not doing this. People may or may not be aware of this. Poor design, development and testing practices caused flaws in software that was running on a radiation therapy system in the 80s, and the result of that was overdoses of radiation, which ended up being fatal for some of the patients. So pretty significant kind of failures of software. Another issue or another incident that was caused by a software problem was the Mars Climate Orbiter at the end of the century, 1999. This was primarily driven a failure to follow inadequate testing of interfaces, and what that did was fail to pick up the fact that two modules were using different units. One was using metric and the other was imperial units. And as a consequence, when the lander was approaching the surface, the distance was being measured incorrectly, and so it crashed, basically. This also related to documentation issues too, because some of the software specifications were not properly documented, and that was picked up. That was missed at some of the issues mission. Just two examples. There's hundreds of examples of failures, but they're pretty consequential. So what are some of the challenges developing scientific applications? So they fall primarily into technical and sociological. Technical, there's issues relating to the fact that the model that you're developing and the software system is itself under pretty intensive research, so it can be changing significantly. Requirements are changing as knowledge grows about what you're trying to do from a scientific point of view. There's some issues with verification and the accuracy of the results, so it can be difficult to verify those results because of representations of numbers. Real world issues are messy things, so typically the software can end up being messy as well. And then there's challenges with the diversity of the hardware that is being used in terms of use and different neuromorphic computing and all sorts of things. So there's a lot of technical challenge that developers of scientific applications are facing. From a sociological point of view, there's issues relating to priorities and incentives, such as sponsors who care more about publications than software quality, and balancing the development of the software with the research. And how much time should you spend on the software engineering aspect of the software versus the research? And if you're working with limited resources, that's a difficult decision to make, because you have to choose one or the other, essentially. And so if it can be difficult to see that improving software engineering and at the expense of doing some of the research may actually be beneficial. Okay, so in terms of best practices for scientific software development, from a baseline point of view, so really these are things that every project should be doing. First and foremost is designing code in an extensible way, particularly for scientific computing, because it's such an experimental process that things are likely to change as you're moving through the experimental process. And to have to redesign everything from scratch every time there's a significant change is going to be very expensive. So building that into the design at the beginning is very important. Version control and automated testing are now pretty ubiquitous, and it's very easy to do this. And you get a lot of benefits from doing it. And we'll talk more about automated testing and continuous integration later, and the benefits of that. Employing rigorous verification and validation is important, and can be done relatively easily now. So getting that at the get-go implemented is definitely beneficial. As is defining coding standards and testing standards and making sure they're done right at the beginning of the project rather than on an ad hoc basis later on. And then there's other policies relating to auditing and maintenance, distribution, how you accept contributions and documentation, many of which are, there's policies around that are easy to adopt. And so you can get some of these into the project at the beginning. Then on the more desirable side, there's issues such as provenance and reproducibility, which even though they have a big impact on the scientific outcomes, it can be much more complicated. And so these are things that you might want to work towards. Lifecycle management in terms of the overall development life cycle, as well as deploying the software. And then a more sort of agile, open development development lifecycle with frequent releases is something that is worthy of moving towards. So many of these things, these improvements to the software process itself, are not typically thought about in the software development lifecycle. And the ideas team has developed some techniques for helping you improve your own software development processes. And there's a bunch of tools and examples of how you can implement these processes yourself and move towards improvements in software processes. And ultimately that helps you improve your software. We're not going to go into this in great detail, but there's plenty of links there that you can follow to if you want to dig more into that. So this is the overall agenda. I've talked about the motivation and overview. I'm going to give a brief discussion or introduction to software testing and some of the terminology, and then I'm going to hand it over to David, and he's going to take you through more complex scenarios and also talk about continuous integration. Okay. Okay, hopefully everyone should see the software testing introduction. Okay, skip the licensing slide. So I'm going to really just be talking about giving you a brief introduction to testing, challenges of it, and some I've run into with testing. There's some examples that we provide. There's some simple ones which you can do in a few minutes, and then a more extensive walkthrough of test-driven development, which we're not going to have time to do today, but we encourage you to look into that. So first of all, I want to start with some general categories of testing. We can break these down into what we call development tests, which essentially are tests that are ensuring that as you make changes to the code, you're preserving the stability of the code. And there's a range of different tests, unit tests, functional tests, and so forth. And I'll talk a little bit more about those on the next slide. Then there's some other types of tests. There are things like smoke tests or post-installation tests, which ensure that the build install process succeeds. And then there are tests such as continuous integration tests, which are essentially aimed at providing rapid feedback to prevent code changes getting into the code base in the first place that might break the code or cause errors in the code. And David will go into that in more detail in a future module. So as I mentioned, some example types of testing, and you may well have come across these before, but they essentially form a hierarchy going from the finest grain to coarser grain tests, but essentially the unit testing where you're testing the functionality of a single routine or module or sorry, not a module, a method or a function at that very fine grain level. When you want to test how those routines or those functions connect together into components, and those components or modules execute correctly, then that's the terminology that's used there as integration testing. And then in order to verify that all those modules work correctly together as a whole, and the program itself operates as correctly as a whole, that's referred to as system testing. And then there's a couple of other kinds of testing. Regression testing is more of a methodology where essentially what you're doing is checking previous results to ensure that you haven't introduced untested changes into the code. And then acceptance testing is another kind of testing similar to system testing, where you're testing the operation the program as a whole, but rather than checking it against, say, the specifications of the software, it's whether the software meets the customer requirements or not. This is just a very small subset of all the different kinds of tests, but these are many of the types of tests that people would use in their software engineering practices. And so it's a good set of tests to know about. Okay. What about verification and validation, which I mentioned? So software engineering and scientific computing both refer to verification and validation, but they tend to use different definitions. So I just wanted to highlight those here. So from a software engineering point of view, essentially verification is checking that the software conforms to the specifications of the software, that is the requirements of the software. From a scientific computing point of view, it essentially extends this to include the mathematical accuracy and stability of the numerical solution. Verification will involve, for example, comparing model solutions to reference solutions or checking for convergence and things like that. So essentially, it's more complex than the software engineering terminology. And similarly, for validation, validation from a software engineering perspective, essentially confirming that the software meets the customer needs. Whereas from a scientific computing perspective, it's more complex. Essentially, it's determining the accuracy of the model, and that's done normally by comparing the outputs of the model with experimental data. However, that assumes that you have the experimental data, and so it's not always, for some real problems, you may not be able to do that. You may not have the experimental data, or you may not have it for certain inputs. In some cases, you have to do more of an indirect method for validation. For example, using the computational model to make predictions that you can then verify. So that's maybe one way that you could do the validation. But I just really wanted to point out here the differences between the two. Okay, so within the scientific development life cycle, it's a very complex process, and it really is broken down into these three domains. I wonder if I can. I was just going to see if I could find a pointer, but I can't. So I'm just going to keep going. So at the top here, you have domain experts that have a set of models and propose, equations required to solve that problem. They also need to think about validation checks arising from the properties of those models. Then in the right-hand part of this diagram, you've got the applied mathematicians who then solvers, for example, to really contribute an understanding to function spaces and convergence criteria to address model fidelity and verify accuracy and stability. And then on the right-hand side, you've got software engineers or computer scientists who are really then trying to map those problem details into programming languages. And they're going to contribute things like extensible interoperable frameworks, things like that, which really contribute to the productivity and performance of the overall application. So this whole team really has to work together effectively and iterate on features to move towards the science objective. So really the point of this slide is really just to point out how complex the software development lifecycle can be in scientific software development. Okay. So within the software development lifecycle, testing is required, at many points in that quite complex lifecycle. But when do you actually write these tests? So often what happens is the tests are left until the last possible moment. You write the code and then you add tests at the end to either meet some requirements or to address deficiencies, or maybe you've encountered a bug and the vendor requires tests to demonstrate the issue. So, it's done at the end of the process. But best practice really dictates that the test should be written before the code is written. And this is known as test-driven development. And one of the advantages of this approach is that when you're developing the code, you're really thinking about what it means for the code to be correct, rather than just what the program should do. If you follow a normal development process, you're thinking about what do I need to do to implement a piece of functionality, and then later on you think about what it means for that program to be correct. TDD flips that on its head and really helps the developer think about that up front, which can lead to better outcomes. But it does have some issues and challenges. In particular, TDD requires the test to run very frequently, and we'll talk more about in the continuous integration module, but that requires you to think about the tests carefully, because those tests need to run frequently. So you need to make sure that they're testing, what they're testing is important, and it's not going to be overly time consuming. Also, the development team needs to be pretty bought into it, across the team. So you can't have some people doing TDD and some people not doing TDD. It doesn't really work. So there are a few challenges, but they're not impossible to overcome. So what does the TDD, the test-driven development cycle look like? So essentially, it's a set of iterative loops, starting with writing a test, and sometimes you can't get away with writing a single test, but in many cases you can. But you are implementing a function, a new function of the program, so you write a test for that function. Obviously, the code doesn't exist yet, so when you run that test, it fails. And then the process is to write just enough code to make that test pass. And this may be an inner iterative loop where you run the test, it fails, you write some more code, and you keep doing that until you get a passing test. Now, the way this works is that you might be not adhering to coding standards, you might not be following interface definitions, you're really just getting the code to work. And so we introduce a step in this outer loop here, which is to refactor the code at this point. So once you have the function implemented and it's passing the test, you then might need to do some cleanups and refactoring to make that acceptable in the code base. And then once you've done that, you have that feature implemented, and you can repeat that, creating a new test for the new functionality, and then repeating that loop. So it's fairly simple, but it's predicated on writing those tests before you write the functionality. Right, some of the challenges of testing complex software systems, and David will go into this in more detail, but they're broken down into essentially designing tests. Complex software tends to be complex, has a lot of interdependencies. It may be difficult to construct tests in some cases because you don't know what the outcome is. The software is exploratory in itself, or you may not know when the model is valid, for example. And then as you're developing the software, you're getting input from domain experts which feed back into the design. So the design may be changing as you're developing the software, and that makes designing the tests a little bit complicated as well, because you need to deal with these issues. Implementing the tests, there can be some challenges there, particularly around legacy code, where here legacy means untested. The original verification may have been lost in the midst of time. Some assumptions and conditions may no longer be known. The goal here is to really understand and progressively improve your code coverage of the code that the tests are covering. And that can be challenging too, in order to achieve that. Couple of other areas, automated testing. It can be difficult to get started because there are so many different options. And then just automating the tests is not necessarily the best thing you want to do. You really need to think about why you want to automate the tests, and then, and that all requires you thinking about what resources are going to be required for that as well. So there's a few different areas that need to be thought about in order to get automated testing working effectively. I'm just going to very briefly talk about how do you figure out what tests are needed. Well, in TDD, you know that you need a test for the piece of functionality that you're implementing, but how do you know what parts of the code are actually being tested or are not being tested? And that's where code coverage tools come in. And there's a variety of tools to be able to do that for different languages. There's graphical front ends, and there's mechanisms for taking automated tests and pushing them up to servers, so that you have an ongoing dashboard of your code coverage, for example. So there's a lot of tooling there, and I'll leave that to you to look into in more detail as you investigate this. So to summarize then, really what we're discussing here is that in order to produce reliable, trustworthy software, because you want to have reliable, trustworthy science, you really need to invest time to thoroughly test the software at all levels. And that includes using automation wherever you can. There are many different challenges associated with the types of codes that we encounter in scientific software, particularly the exploratory nature of the software, but also there's a lot of legacy software around as well. And so those challenges, are something that we need to take on board and figure out solutions to. It's not, there's a lot of solutions out there now to help you adapt, to fit whatever your particular situation is. And even though there are so many technologies out there, the important thing is not to get distracted by them. And really what you want to do is get some tests going, get some scaffolding into your project so that the testing is working, and then focus on the code coverage and getting the tests in there. And if that means just adopting, like just finding a particular technology and adopting it and running with it, then that's the best way to get started on this. There's more resources for if you want to go further on code coverage and other testing frameworks. And then there is the hands-on examples, which you can basically, there's a bunch of slides here. You can just follow through those if you would like to take the hands-on examples further. Okay, I'm going to stop at this point and I'm going to hand it over to David.
Thanks, Greg.
I apologize for we're about 5 minutes behind.
Not too bad. All right, so I'm David Rogers, and I'll take off with the second part of this tutorial on testing complex software and continuous integration. I want to give a quick thank you to the members of the Ideas team for helping construct all of these slides and the tutorial material, and especially David Bernhold for getting us organized in how we're presenting these things. The tutorial wouldn't have been possible without everyone's input. And with that, let's get started on the complex software testing intro. We have our preferred citation and license, etc. And on complex software testing, it's pretty much the same as intro software testing, and there's the same definitions and guidelines and ideas. But with this one, we're thinking more of if you have a large team, or if you have some initial tests and a working code base, and you want to start scaling and thinking about, how do I know when my tests are done? How do I construct my test suite in a way that allows for expansion and thinks about some of the later hurdles that I'm going to go through? And so this presentation has a couple of use cases and stories that will talk us through those ideas. Like we've heard before, there are a couple of levels of testing that you want to think about. Automated or scheduled testing is the one that's maybe the one that we're more familiar with, that because we're used to working on Linux command line terminals, etc. These are maybe indefinitely long-running tests that can use the hardware, like the production hardware that we want to run our test suites on. And they're designed to provide comprehensive coverage and show us really that our results are validated and working the way we expect them to. Continuous integration, I want to distinguish from automated and scheduled testing as something that's automated, but is built in such a way that it allows you to quickly diagnose error so that you can see at a glance or with a very simple test whether or not your code base is valid and compiling and things are working. These are the sort of the things that go into continuous integration tests are the sort of things that computer scientists usually think of, like does the API interface work as expected, and what are my function types, and is everything compiling? In practice, there are some rules of thumb that you want to keep in mind when you're building tests. All your tests should be as simple as possible. Complex tests really have to have a great reason to exist in your test suite. If you can make your tests simple and kind of build on each other in a very logical way, then you can quickly pinpoint errors in your code. You also want to have your tests have a mixture of different granularities. So think about unit tests that start at testing the individual functions or data structures, moving all the way through integration tests, which are testing whether different pieces of your code interoperate correctly or your code with someone else's code, and restart tests, which are right obviously in the middle of a campaign run. The lights go out and you have to restart your computation. Is that restart going to work the way you expect it to? Okay, you might be tempted to get overly creative with test cases to try on every possible scenario in a test, but that can be counterproductive because when you spend time on creating and maintaining your tests, that can take away from your team resources to get other things done. Ideally, you want your tests closely aligned with the science objectives for your single domain codes. That the tests will give you baselines, and they'll give you kind of checks that your science code is doing what it's supposed to be doing. If your test goes too far away from that or expands, then it can distract your project. Or for multi-domain general purpose code, your collection of tests should maximize your coverage while minimizing the cost of developing and running the tests. The elusive goal that we're striving for. On the other hand, you also want to make sure that there is enough testing and that you have coverage of the different modules in your code where things might go awry, kind of have an eye or use a domain expert or pull in somebody who can help tell you where your tests are most likely to fail. And this is where your team can start thinking about getting a meeting that focuses on creating a testing plan. The goal of a meeting for creating a testing plan is actually just to clearly map out what are the expected uses of the code. What are the parts of the code that are critical for long-term stability and that are going to be imported by every other module and that are going to have to be really hardened so that everything that's based on them can thrive and function, and that you don't have to keep going back into low levels of the code and debugging them. It's also important at that meeting to establish who on your team should be responsible for ensuring that each piece of your code works. And are there additional difficulties coming from the interaction between modules or between different subteams? And of course, how can you reasonably address those? For example, so here's a nice picture of a Halo exchange with a couple of MPI ranks and some Halo cells that are overlapping. Users of a particular library might assume that this overlap region between processors is communicated correctly during a Halo exchange. But if there's no test that tries that out with a varying Halo size, then really there's no way to know when the assumption breaks down. So the line of thought, this line of thought really helps you get at the perspective of, we have a couple of functionalities that our code is going to be based on. Let's figure out when things are going to break and make a testing plan that addresses those things to make sure that we can pass our stability on to our users. Okay. I think I already talked about the team meeting a little bit and what you should consider when doing this. So I'm going to keep moving. Additional tests on good testing practices. If everyone is on board with your testing plan, your code is in a good place, what happens next? You can double check your work using a code coverage tool. Gcov is one that's built right into the GCC compiler. And if you are unfamiliar with that, then check out some of our tutorials or docs there. It's pretty easy to get up and running. You can create a policy on what to do with failed tests and issues marked as bugs. A lot of us are tracking our code issues through GitHub or GitLab issues. So when you get those issues, maybe if you have a team process for marking those issues and triaging them or for assigning them, that can make sure that things happen. And also that it helps you to put names on these tasks so that you can recognize the hard work that's put in by that team member who really keeps things going. You should consider your test suite when you're refactoring your code, because once you have a great working test suite, it starts becoming useful in a variety of other things. If you're performance optimizing, or if you're refactoring, or if you're doing a release, that the test suite will give you confidence that issues aren't going to creep through into your release process, which can be expensive to maintain and fix later. And nobody wants to go back supporting previous releases when you're trying to push forward the next new feature release. Now I'm going to go through a couple of examples that talk about testing in practice in a couple of scenarios that are gathered from team experiences. So many of these ideas come from our ideas project member Anshu Dubey's work with the E3SM and flashcodes. Example one is an ideal case. You're developing a new code and you develop your diagnostics as you're developing the code itself. So this is the test-driven development that we heard about from Greg. You're incorporating the tests and hopefully the documentation right next to your code. And you can now, usually people do this while they're writing a piece of code. They'll run it a couple times interactively. But if you take the extra time to recognize that those interactive sessions that you're trying things out with are tests, if you take the time to harden those tests and save them as test one, test two inside of a file, that can go turn into your test suite and save you headaches later. As your package gets more complex, it becomes non-trivial to design good tests. And so as you build your functionality and refactor your code, you should probably also find that you're refactoring your test suite. Importantly here, proper testing procedures can also help encourage new contributors to your code. So only recently I had this experience contributing a feature to a code called Alpaca. The first thing I did was check that the team actually wanted the feature by asking them inside of the issues requests on their GitLab, GitHub, and then they said, yeah, sure, go and add that feature. And so I ran their test suite locally, added the feature, adapted one of their existing tests so that I could test my new feature, and everything was working. So I was able to push it into the main repository and have some really good confidence that it was going to work once it was put in. All right, so example two is when you're testing or working with a legacy code. That's defined as a code which is out there and has lots of parts, but doesn't necessarily have all those parts tested. Or maybe the tests are lost in the midst of time. Let's see, so there are a couple of strategies that actually have worked with adding tests into legacy codes. And the one that I'm showing here has this picture of a tree that's schematically showing the code tree. So we might think of this state here that's sitting inside of these two branches as a state that is needed, a state of the simulation system that is needed to exercise this part of the code down here. So here there's maybe a function or a module or a time step that needs information from this state to do its job. This state, of course, sits inside of a larger pieces of code. And so in order to effectively integrate tests into this code, rather than running the entire code, which maybe takes a couple of hours on a supercomputer, the idea is to run the code once and capture the state and save it as a file. And so you have to do some file IO to capture the state. And now you have these modules that you want to exercise. But in real world case, you can't just exercise a couple modules. Sometimes you have parts of the code that are containing constants that you have to cut and paste over here. And sometimes you have a part of a code that needs to be modified somewhat so that it's not connected as much to all the other pieces, and that you're able to run it as an isolated test. And so you can bring in, kind of port these other pieces of the code so the external dependencies in the code so that they're able to provide what they need to provide, and then turn a test driver which loads up and then incorporate them into a test driver, which loads up the state, exercises the piece of code, and gives you a pass-fail result by comparing to its known result. And it looks like this is a complicated process, but in this case, it turned out to be worth the effort, because what used to take several hours on a supercomputer was turned into a couple of minutes on a developer laptop in order to be able to test this important hotspot in the code and do performance optimization. Example 3 is when is coming from a code which is starting to grow larger and larger and refactor. And so here in the Flash code, they had a couple of modules that are like the physics that happens at an individual grid point, and then the grid points themselves, and I believe there's also like a halo exchange between those grid points. And so the idea of refactoring the tests in this case was to start to think about the modules and how they interoperate with each other, so that if we want to test, say, just an individual grid point, then whatever it needs as a dependency is going to be a kind of a mocked dependency. And so that by taking out this piece of code and making all of its dependencies mock dependencies, we can test it in isolation from every other part of the code. Once we have that, we've got kind of our lowest level of test. We can build on this test and exercise it inside of other tests. And so now if we have something that's sweeping across grid points, we can use our actual physics that's happening inside the grid point as a dependency in a unit test at a higher level. And if we go to even higher levels, we can use these kind of we can use the scaffolding as it's building up so that we're able to get larger and larger scale tests with more of the real code in there. But at the basic level, we have to mock up a few dependencies so that we don't have an intractable graph of tests where we can't pinpoint failures. All right, so in example 3, continued, I'm going to show that I guess those different parts of the test are the guard cell fills versus halos. And actually, maybe I'll skip over this in the interest of time with all the nitty-gritty details, because I've explained the basic idea. But there are tests for individual pieces which are isolated, and then there's a test which is able to exercise both of those tests together. So we may also have, say, hydrodynamics inside the Flash code, which is using guard cell tests for halo exchanges and equation of states tests for the physics inside the grid point, and then can run hydrodynamics that uses both of those. And of course, if you're using hydrodynamics, you might want to do adaptive mesh refinement. You want to start by testing without the adaptive mesh refinement and then add adaptive mesh refinement. And so this is the idea that you can start to build up more and more complex features when you turn them on. And if any one of those features fails, so for example, if you're doing dynamic refinement and changing your grid as a function of time as your simulation proceeds and it fails, well, you don't know where the error is unless you already ran a test that said that you did adaptive mesh refinement without dynamics. And if this one passes and you know that adaptive mesh refinement works, but you haven't done dynamic refinement, then the error must have been in something that happened dynamically. So this is the sort of idea of adding functions one at a time, adding functionality one at a time. So you can pinpoint exactly where the error occurs. Check my time. Okay. So example 4 is maybe a look at what is the definition of done with regard to a test suite. In this case, also coming from the Flash code, the team had a couple of meetings to try and figure out, when is our code done and what have we tested and what have we not tested, and what about our users and our academic users and our downstream products, are they actually getting what they need out of this code? So what they ended up doing to figure out the definition of done is writing down a grid with functionality, kind of physics functionality along the top. and different modules of the code or mathematical functionality along the rows. And inside the grid, then they just kind of took all the unit tests from the simplest unit test to figure out what it's doing, all the way up to the most complicated tests. And they took each test and said, okay, this CL test is able to test adaptive mesh refinement inside of each one of these physics cases. And then they can write it down and fill in all the spots on their grid. Look at the next test, do the same thing. And by the end, you have a map of what tests are looking at what physics functionality using what modules of the code. You can now use this and convey it to your academic users or to your sponsors and say, here are the parts of the code that we've tested. Maybe we didn't test AMR with gravity, but there's probably a physical reason for that. We don't ever use that combination, something like that. And this sort of grid helps you structure, where have we spent our time testing and where have we not needed to focus tests, et cetera. You can also spot an open, an open place that you meant to do testing but didn't quite have it. And that gives you an opportunity to develop a new test that just covers that one thing you need. Okay, I threw in a couple of slides here. This is a larger part of a presentation that the ideas team usually gives that has a couple more modules. And what I'm doing here is I'm putting a couple of slides in from the reproducibility module in order to give you a sense of where testing might fit into kind of a larger picture of reproducibility inside of scientific computing. And so see, one of the things we'd really like to accomplish with better testing practices is actually just more reproducible and reliable science, because the time spent on testing competes with some other important goals. It's good to be able to communicate the value of good testing. And here's one way to do it, that by investing in some of these reproducibility or testing functionalities in your code, you can enable kind of more transparent and understandable science, which other teams can utilize and reproduce better. And you can communicate that has been accomplished to your sponsors, who can now say, okay, we were really justified in funding you to add on to your regular set of things that you do, extra work and time and effort to get your code into a shape where it's more easily reproducible by others. Long-term, these sorts of communications and telling everyone about this and explaining it about your code is hopefully going to help us change the way that people view what is a good science paper and what is a good science code. Additional motivation for testing practices. Tests can give you confidence that your code is working without trying to repeat the runs. In some places, repeating runs is impossible. It's kind of difficult on special purpose hardware, which only has a limited number of cycles. So yeah, on very large projects and places which are using big resources, you really want to have a good test suite, because it prevents you from using excess cycles there. I'm going to skip over kind of fast some of these other slides, but they're present in our online tutorials in our online material that's linked with these presentation slides. They help you to kind of build up a questionnaire or kind of a mind map of what's happening with our testing strategy and what other things might we want to consider. Numerical artifacts, planning ahead for your progressive experimental campaign, checkpointing and restart, all of that extra functionality. And then also different kinds of tests that are maybe based on physics or designing by contract, which is testing inputs and outputs of your routines, testing third-party dependencies, testing your hardware environment, testing regularly with CI, which I'll talk about in a minute, or being creative with tests that are maybe making up synthetic data, et cetera. All right, so takeaways on testing. We looked at the context and motivation. We looked at kind of the cost of tests and how to maximize the impact of time that's spent on developing and running the tests by making sure that every test can pinpoint the exact source of where the error is occurring, and it gives you a hint as to what to fix in the code. And we also looked at different scenarios where your testing strategies might be different and kind of informed by where your code is and what your objectives are for releasing your code to the public. it's important to kind of maintain that holistic validation strategy of what is the global context that my code is being used in, and what are the most important core modules, and how do I structure my tests to get a maximum impact that way. I'm not sure if I have too much time for questions, but if you want to interrupt me and ask questions, go ahead. I can't actually see the chat right now.
There's no questions in the chat.
Okay, so I'll move on to continuous integration. Now we'll talk about the CI for making a neat interface and workflow for watching all the tests that you've worked so hard to create. Here's our license slide. First, what is CI? We're all familiar with this idea, inserting a check into the development workflow. This talk is actually part explanatory and part walkthrough on what's out there and how it works. So this is GitLab's nice timeline view. The basic Git usage is to commit your changes to a feature branch. If you're not making feature branches for adding new features or for working locally on your code, this is like level 0 of getting started with using Git to help you track what's changed in your code and how. Create a new feature branch and make your changes there. Commit to your feature branch and push those changes to your code repository. Now, CI happens after you push that code to a code repository, where the idea is that the system that's hosting your code repository will be able to automatically take your code, pick it up, build it, and run it, and tell you whether or not the tests that you've incorporated into your code are passing or failing. Hopefully, it gives you enough output to tell you where the error occurred. And also, hopefully, the process of running CI is not too much of a burden, so that it's difficult to tell, if the error was in the CI system or if the error was in your code itself. In most cases, CI systems are simple and give you this nice, text document of what happened and what test was failing, plus this red X, which reminds you that, yeah, I need to fix something. So you push a code fix on the same branch that you pushed before, make the change, push it up to your repository, the test runs again. Finally, you get that thing to pass and you can review and approve it, and finally merge it into whatever next release branch or main branch or development branch that you're building collaboratively. CI can also happen at the deployment stage where, but because you have tests already, you can also run the tests on the main branch, which is the subject of everyone's development, just to double check that it's still working after you've put all of your features in. Developers that have adopted CI once in one project, they often carry that workflow over to their next project. And we think that's because CI gives you a fast check on the code's working state. It's like keeping your checkbook balanced. And when you keep the checkbook balanced, you can look back to the last point when everything matched up and was good. And it makes tracking down the errors become simpler. You don't have to check, a very large space of code commits. This also means that CI tests should be fast and include infrastructure like the build and integration scripts. And it also means developers should merge often and CI should be run continuously. So the idea here is a fast test, which is focused on the critical functionalities that your testing should use, and not too much duplication. Let's see, and that encourages developers to develop and then test and then merge and develop, test, and merge, etc. It's continuous so that it can be run automatically, so that this test step kind of happens during the merge step, and it's a little bit less cognitive load in order to make sure that your tests are running. CI generally implies lots of automation. Let's see, I want to distinguish continuous integration with a couple of other buzzwords that are out there. There's test or documentation-driven development, and I guess there's different opinions on the matter. Some people are test-driven development, and some people are like me, are documentation-driven development. But the key idea here is that you keep your tests and your documentation consistent and up to date with your code. Let's see. For test-driven development, the initial CI shows the failing tests and the code commits trigger retesting. And for both, the developers keep the tests and documentation consistent with the code. Automated testing is software that automatically runs your tests on a regular basis and reliably detects and reports their kind of strange behaviors or outcomes. That doesn't necessarily mean that it's inserted into the development workflow. So continuous integration is the next step where you have a script that runs your tests, but that script is run on every commit. So it happens kind of at high frequency, and it's aimed at preventing the code changes from breaking the branches that's inside the development workflow. I'm going to show you on the next slide some examples. So there are some automated test suites that you might have heard of, or you probably have your own automated test suite if you're on a sufficiently large project. That's the shell script that sits in some test directory that says run me to check for tests, and it might be run on a weekly or daily basis by some system that sits inside inside of a job or on your supercomputer. And usually you kind of script those up. On your own. So I scripted one up. Flash has one that they've scripted up and gives you a nice output based on what kind of functionality is being tested in the code. These things can be compute intensive and kind of longer running, and have maybe a ticket interface where you get a ticket, like a job ticket, that tells you here's a bunch of stuff that's running, and check on me later and I'll tell you whether or not it finished correctly or not. CI testing is meant to be very fast and live kind of embedded in your development work. And that's usually run at the GitHub or GitLab server level. So they'll provide a virtual machine, and you can run on that virtual machine just a quick script, which will give you a yes or no without maybe moving off of GitLab or GitHub servers. Before you start coding up some YAML files to make the tests happen, you want to consider what fast checks mean to your team. Usually projects start off by just building and installing their code, and that checks for things like syntax errors. But next up, though, you'll actually have to start figuring out what parts of your existing test work with CI and how you'll cover your code base. So some of them you might actually end up dividing your tests. So some of your tests go into the CI tests, and some of them go into like scheduled, longer running or job scheduled tests. You can get snagged by some advanced situations like bit for bit comparisons that can be machine dependent. So you have to watch out for those. You also might get stuck if your dependencies take a long time to compile. And some tests might consume too many resources, and especially kind of performance tests or things with very large resource files. I'm going to give a couple of pictures of where tests run before I get down into specifics of what YAML files do and how they run. And these pictures of where things go are helpful in mapping out, like, where does this YAML file go and what is it doing once I write it. As an ORL developer, I'd like my tests to run on the supercomputers here to match the production environment. But in reality, CI is actually much better cut out for running on like an x86 virtual machine that I can get for free from the cloud. Tests that run on the HPC cluster probably need a special scripting setup. The free resources here are like GitHub, Bitbucket, GitLab, all of which you should be familiar with, that provide shared runners. Those runners are, of course, running on the virtual machines provided by the cloud, and will give you like a base operating system, but not no advanced hardware and limited memory as well. So those constraints kind of keep your testing size down. You might also have site local resources, and in this conference, you'll hear about developments from the ECP continuous integration team on that front. Hopefully you talk to the local experts on doing CI integration before you start scaling up your tests. And probably the end result for all of us is going to be to maintain a couple of different testing suites that run on different systems, right? You've got your fast CI tests that run on the cloud, and you have your kind of medium weight CI tests that can run on local resources that are more like your production. And then you've got your production tests, which are really going to have to be scheduled tested. Okay, so now that I've covered some content and also given a shout out to the ECP CI team, who is building great stuff, I'm going to go on to a picture of how this all can work in kind of the network map space, or the data flow picture. You're usually creating a bunch of code commits, which are going out to your lab or university, which probably has its own GitLab or Bitbucket setup. That lab or university may not necessarily want to communicate very much with the outside world, so there's usually a big firewall that's stuck there. You can talk directly to GitHub But this probably should be part of a release process that you should need to check on at your organization. So, develop locally and then periodically push those releases to GitHub. Both of these can usually do, and I'm saying usually a lot because you have to talk to your individual sites on how they're set up. But the default setups in GitLab and GitHub are both able to integrate with CI runners, which are running on virtual machines. And so this local area will give you, a test that runs locally. GitHub can also run local tests. You can incorporate third parties into this because GitHub is able to set up, and GitLab also are able to set up what are called commit hooks. And those hooks basically just kick off REST HTTP API requests. So you can, if you want to ask cloud providers like Azure or Amazon or Google for some build service nodes, then you can configure those build service nodes and have your push code over to them to compile and run. And that can give you, a little bit more resources sometimes. Of course, then you get some extra arrows of things you have to communicate with. Codecov.io gives you a nice graphical summary of where the test coverage happened inside your code source files. And the way that works is actually a full integration with GitHub. So it's not just pushing off an HTTP, it's not just pushing off an API hook on a commit. It's also pulling information back from Codecov that it can display directly inside your pull request. So let's see. Now that we've covered the where, I'll talk a little bit about the what. You'll want to get started with something like a hello world continuous integration definition file, for which I'll show an example in a second. That file will basically pull in some dependencies and then run the make script that's already attached to your source code. And then it should run the test binary. So think about, at this stage, when you're creating the CI file, what are the dependencies that my code needs to pull in? And what are the configurations that my code's going to run in? So do I need to test different compilers? Is MPI one of the critical components? And can I install it? Basically, if you need MPI, or if you need MPI, then you would pull this in with an apt-get inside the usual machine configuration. With Python, you can install it a couple different ways and find a lot of examples of how to compile it. You also want to ask what functionality in my source code is most important when you're configuring your tests. If you need advanced hardware, it becomes a little bit more difficult because of hardware availability. And some good candidates are kind of what I've shown here. Just start with the simplest possible thing and build on that. Okay, so different CI providers have a different YAML file keywords. And I'm showing here, different services that you might find out there. And they're pretty much all YAML files that live in different places in your repository, but basically accomplish the same things. They all do download, setup, build, and run. And they might have different keywords for those. So just find an example and check the documentation, and you'll be able to get started without a problem. For GitHub Actions, the next few slides will show that syntax. But GitLabs is really very similar. The key points here are that YAML, which is yet another markup language, is like a more friendly JSON syntax. If you're familiar with JSON, that would make sense to you. If you're not, then it consists of JSON objects, which are key value pairs. The JSON objects show up either as brace lists or as indentation. So on : means that on is the key, and then everything inside this indentation level, all this stuff, this is the value. And then push is another key value pair, pull request key value pair. There are also lists, so things inside of brackets. You can use a bracket to make a list, or you can use a dash at the beginning of a line. So these two syntaxes are equivalent for the lists. And as kind of the leaf nodes of your syntax, you either have strings, check results turns into a string here, or you have integers. You can also have nuns, because there's like a null object inside of JavaScript, but pretty much nobody puts in the nuns. All right. Here I'm showing a couple of the outer syntax of the GitHub Actions file, which is defining when do I run, so what conditions do I run on? And here the example is giving us run on a push to the main branch or run on a pull request to the main branch. The pushes would come from when you directly push with git git push. The pull request is when you push to a branch and then you pull request it into main because you want to do some reviews and checks on it. And this pull request mechanism is the one that I'm advocating here with feature branches. Jobs are the steps that happen when the CI run is triggered. And so there's a build job, which is going to have a few steps that make that happen. After this is triggered and each job runs, you'll see a graphical summary that looks like this. So here's the build job that's been run, and here are the individual steps. So you have setup job, run checkout, make coverage, and that's just the output of each one of these individual steps. Set up the job, the checkout, make coverage, and upload coverage. Because I'm showing here a upload or a coverage action, GitHub has these actions that you can read the documentations for what the actions do. This one is a coverage action which talks to codecov.io. And in our example tutorial, we show you how to set all that up. It's just you have to talk to codecov.io to tell them that you want to integrate. And then you can also see the summary of what individual source files have what amount of coverage in this pull request. All right, so we've covered what the YAML file is, how it looks when you run it on the server, how it's triggered. Over time, you'll be able to build up a history of the tests that have run, and you can see that history inside of GitHub's Actions tab. So you'll notice at the top of GitHub, there's different tabs. There's also a tab inside of GitLab, which will give you the history. And when you look through this history, you can see what branches and what tests are working at what point in time. So this gives you kind of a nice kind of summary of where your project status is. I already went over a little bit of what are the key objects, key elements defining tests, so I don't have to spend too much time on this, but I did want to give you a more advanced example. So the stuff that I'm showing in these slides is pulled directly from the Pyomo project, which started with a very basic setup like I'm advocating, but then it grew from there into doing a little bit more things. So there's some more advanced syntax. It still has a name, it still has an explanation of when the tests are going to run. And here it's showing like an extra workflow dispatch keyword that says, let's just manually trigger when I have a git ref. So there are other ways that you can start tests. Also, there are more advanced options that you can use in your job setup. What you're seeing here is that they've actually named their job with a template. So this $brace syntax is going to substitute in matrix.target Python other. And those are coming from here, where we've defined a matrix of tests which have different values for OS, different values for the Python version, and they haven't been using other, but this matrix of tests now allows them to look across different operating systems and different versions of Python. I also want to point out that these operating system versions, you'll find in the documentation which operating systems you're able to use. Here it's just a keyword, but in fact, let's see. Here it's a keyword, but later on there's actually there's a way to turn that keyword into the base image for the container that the tests are running in. So the way that they're using their setup, this keyword turns into the selecting the container. And there's a connection with containers and tests here that's a little bit off topic to get into, so I won't get too much into detail of it, but other than to say, your tests are running inside of containers, and you have the ability to pull in containers from different places and customize those containers kind of outside the testing process, and then start with them when you run these scripts. Okay, and so to continue on with the advanced example, there's a matrix of tests, and the script is more complicated, but you can see that it's still doing, download, setup, build, and test, and it's just using its substituted values to accomplish running this matrix of tests once for each combination. All right, so we've given an overview of what tests are what's out there in terms of testing. And here I want to just give you some aspirations to help your team pick out the next steps that will work best for it. The guiding principle is to reduce barriers to developing and testing and deploying your code. So if you're adding a complicated testing process that you don't need, you're probably overdoing it. But if you have a regular process that you want to test, then finding a way to automate that and get it so that it requires a minimum amount of effort is a worthwhile goal. Ultimately, it should give you a faster pathway to scientific productivity. And with that in mind, I suggest looking at ways to make your local tests mirror what your remote CI process looks like. And that can include a container solution, as shown here in kind of like the Docker best practices guide, where they say that if you use a base image, which is, including all of its dependencies already, the E4S provides some base images that you might want to have a look at. Then you can run your tests locally inside your base image, but also run your tests remotely inside the same base image. And then the outer loop kind of runs and manages the deployment of your testing. See, caching is also something to investigate if you want to try and speed up your build, but don't necessarily go too far into any one of these options unless you really need it, because complexity versus difficulty versus payoff. Okay. So overall, CI reduces the number of issues that can escape your feature branches. Running CI quickly helps keep it relevant and useful. Splitting up your test suite into fast and scheduled tests can take a little bit of work though. So you really ought to have a planning meeting to think through what is your testing strategy before you start making that jump. CI is a natural fit for test-driven development and also for building the documentation. There's a lot of good recipes out there that will show you how to take documentation that's right next to your code and build it as part of your build and release process. There are a lot of ways and means to make your tests run once you have your set of tests defined. So in fact, a lot of the work here is not actually the CI part, but it's just working locally with your code base to have a nice test runner. There was a talk earlier today on using CTest inside of your CMake workflow. I would recommend trying to do that if you're using CMake. And there are other test frameworks out there that can make the burden simpler. Starting out is pretty easy, and once you have a working example, then you can build on it. All right, it looks like I went through several of those slides kind of fast and made up some time. So I'm going to go through a couple of summary slides, and then we'll have time for questions at the end. This afternoon, we covered motivation. We covered simple and advanced testing, as well as some CI strategies that your team can start to think through. Here's our licensing acknowledgement slide. I want to note here that testing has cumulative positive effects that extend well beyond your project. Testing is a part of a good developing practice that provides confidence in the results of your team, but also in the results of teams that are depending on you. You'll notice that that's important, increasingly important across the software ecosystem as project dependencies get built up across the ECP teams. So SPAC is doing CI that relies on your test suite for its tests to mean as much as they possibly can. But then there are software development kits or E4S SPAC tests that are being built on top of SPAC CI, which is built on your test suite. And the E4S release process can be pushed out to facilities, or facilities may be depending directly on SPAC tests, et cetera. And so all of these tests are cumulative, and they provide a lot of value kind of to the entire community. We covered these software engineering topics, and even though we talked about these areas, there were a lot of areas that we weren't able to have time for in the tutorial today. So I'm going to mention, good documentation, licensing, packaging, and distribution. These are all things that are good to formulate a strategy around and kind of be aware of the space of options and what's out there. And we have some materials on those that you can find in our other tutorials online. And we welcome questions on those areas too. A last note that I want to leave you with is that the trade-off between investing time in testing and adding features and doing the science. And as a researcher, obviously you can't afford to spend all of your time on software engineering because real-world projects already have lots of milestones, requirements, and motivators. So you might be asking, how do I start? Working with my team on adding more of process Y. Fill in process Y here. Greg mentioned this, and I'm going to come back to it and mention it a little bit more now. we have for a while advocated the use of PSIP, which is productivity and sustainability improvement planning. And the productivity and sustainability improvement planning is, let's see, it's like agile for processes. In a nutshell, you ask your team to have a meeting that's just devoted to identifying its development and science output process pain points. Those are things like, our tests are always failing or failing more often on this system, or whenever we add this kind of feature, we end up getting stuck in design arguments too long, or our documentation is usually slipping out of sync and we have a whole lot of users requesting us to fix the documentation. And so if you have a meeting and you all think together about which one of those process pain points are the ones that are highest on your list, then start to compare them, then you get some of these issues to a point where your team can start to think, well, okay, we need to spend a little bit of time just defining goals on what this process would look like if we did it the absolute best that we could. We have, the team has developed a assessment tool, rateyourproject.org, that's a questionnaire if you want some introspection on good, maybe some good process questions that you can all go through and discuss. It gives you some ideas in case you're having trouble finding terminology for those pain points. However, once you've had this meeting, your job is just to kind of work together to set a goal. When you set this goal for what you want to improve, then you're targeting kind of what does the outcome look like? What is our behavior of the team going to be in the future? And then write it down on what's called a project tracking card. There are example project tracking cards at this repository, bsswpsip.github.io in the catalog. And if you have developed a progress tracking card that that is new and doesn't fit in any of those categories, then we encourage you to submit it for consideration to add to our catalog so that other teams can benefit from adding that process as well. Or you can take one of these cards and adapt it. You definitely want to adapt it to what your team's goals are and what you want to do. And then as you work on your plan, you're kind of tracking and coming back to revisit and revise your progress or goals. Pretty much like the agile process, but you're focusing on the goals that you want, the goals and process that you want your team to adopt. And of course, the idea behind all of these processes like CI or like better documentation is that once you've adopted the process, it takes a little bit of time and effort, but it makes your costs go down to completion of your project. All right. Here are some ways to get more information on the Ideas ECP project, the project members, things that we're doing. I want to especially point out our online tutorials and walkthroughs, as I mentioned a couple of times. They'll give you some simple code base to practice these steps on so that you can get a quick sense of how all these things work in a small code base before you go and apply them to the real code bases that are out there. Having that kind of experience of here's how it's supposed to work lets you, fix all the bits a little bit better when you're scaling up. Also, I'm going to point out a couple of related events from our team at the ECP annual meeting. These are all Eastern times. We have an Ideas Help Desk, which is in room 125 of the side meetings of GatherTown. Just like in real meetings, we've had, I guess, a couple of glitches with using GatherTown that we saw on our ECP Slack. So hopefully we're working on those glitches with meeting areas and finding the rooms, etc. But it gives you a little bit of the real conference experience. And we should be there 12:30 to 1:30 Monday through Friday. Let's see. There's a broader engagement initiative talk on Tuesday. There are a couple of, there's the AD hardware integration and facilities poster session that our team has posters at on Tuesday. There's best practices breakout Wednesday, as well as a panel on sustainability VCP software and applications Wednesday. And Thursday, we have the PSIP team talking with a couple of VCP projects on the team of teams principles, which are ways of thinking about how multiple teams can interact together in a productive way to kind of build an ecosystem together. And as a bonus, there is Wednesday, 11th of May, an ECP Community Birds of a Feather Days on software, fostering software sustainability. That is through bssw.io and requires registration. So be looking for those opportunities. And with that, thanks everybody for a great tutorial today. And let's maybe have a few minutes for questions.
Hey, David, there's one question in the chat. You might want to tackle this one. It's any suggestions for making software project documentation more automatic?
I've put together, and I'm not sure if I put the links in here. I have an example of a CMake which will run the Sphinx documentation tool as one of its steps. So it's Doxygen plus Sphinx. So you use Doxygen to get a bunch of XML files, and then you use Sphinx to format those into a neat Sphinx RST. And it's all run through like a CMake external program target. And I will provide the link. Provide the link for that. It's out there, so I'm going to assert that it's existing, and I'll see if I can type it in really quick here.
Okay. Yeah, I think just using something like Doxygen would be a good starting point. I mean, that does a certain type of documentation, really depends what you want. But if you're just looking to document your APIs and your functions and so forth, then something like Doxygen is pretty good for that. But if you're talking about user documentation or developer documentation, then that can be more problematic. It looks like Jim has his hand up.
Hey, David and Greg, thank you. So I had one question about what David was saying concerning mock objects and building up a testing framework there. You mentioned once you have the mock objects established that you can have those tests build upon one another to some extent. It wasn't clear to me if you were talking about just having kind of standard integration tests, or if you were talking about essentially having situations where you replaced mock objects with real objects to achieve integration tests, or if there was something else that you were getting at when you were saying that.
So I was mainly talking about code that you control, but I suppose it's harder to do with integration tests, right? Because with code you control, you can build a mock module that just provides the basic API, and that'll work. But with integration tests, you'd be talking about, kind of mocking up an external dependency, which could be a lot of effort or not. So maybe it depends more on effort than whether it's internal versus external.
Right, thanks.
Another question, which Mark, thanks Mark for copying over from Hoover. Can you suggest a strategy to minimize the amount of CI provider specific coding?
I haven't found one. I do know a couple of teams that have said it's a pain point to switch over from Travis CI to GitHub workflows. But it's the same basic steps, and I would say the most defensive strategy here is to maintain scripts which do a lot of the work as part of your code, right? Because then the CI can be minimal.
Yeah, unfortunately, they all seem to do it in a completely different way. So GitHub is very different to GitLab. I mean, the concept's the same, but the code is completely different. So that can be pretty painful. Another question is, how much churn is there in CI provider space such that projects have to constantly respond to changes being made there?
I haven't seen a lot of churn. For now, there's GitHub, GitLab. I think Bitbucket Atlassian has a solution. But for getting started, it's not too difficult. For switching over an existing CI pipeline, this is where you have trouble. And I think maybe you'd expect every 3 years to have to switch over your CI pipeline based on what I've seen.
I think that's all the questions from the chat.
I think we're out of time too, so I'm going to stop the recording, and I think everyone's welcome to stay on and continue the discussion as long as they like.
Thanks.
Thanks to Greg and David for presenting today.
Thanks everyone for coming along.